Hello and welcome to this video for OCR A-Level Physics, where we're going to be looking at acceleration due to freefall, which is part of the forces of motion module with our subtopic of motion. So in today's lesson, we're going to be looking at how to calculate the acceleration due to gravity from an object in freefall. So if we've been successful and we've learnt in today's lesson, we should be able to understand that an object in freefall experiences an acceleration of g, calculate the values for an object in freefall with the equations of motion, and explain why an object in freefall undergoes constant acceleration. So we're going to be looking at the following parts of the OCR A-Level Physics specification, in particular acceleration g of freefall. So in the previous lesson we looked at the equations of motion, which are v equals u plus at, s equals ut plus a half at squared, s equals a half u plus v times by t, and v squared equals u squared plus 2as. Now we can use these equations to describe the motion of an object in the real world. Now this can include an object free falling. Now freefall is when an object accelerates towards the ground due to the resultant force of gravity and no other forces act on the object. So for an object in freefall, there is gravity acting on the object and nothing else. So we know the object is undergoing an acceleration of g. Now acceleration is a vector quantity and g acts towards the centre of mass of the Earth, the centre of the Earth's gravitational field, which we perceive as downwards. Now the magnitude of g is 9.81 meters per second squared, but this does vary slightly over the surface of the Earth. Now the value of g does vary depending on factors including altitude, latitude and the geology of the area. So for example, g in Helsinki is 9.825, in London it's 9.816, and in Singapore it's 9.776 meters per second squared. Now we know that when an object is undergoing freefall, the only force acting on this object is its weight. Now we can see that objects can have an initial velocity in any direction and still undergo freefall as long as the force that's provided the initial velocity no longer acts on the object. So we know that all objects in freefall accelerate to the ground at the same rate. Now the scientist who investigated objects falling freely was Galileo. So Galileo set up systematic and rigorous experiments to test his theories, and these experiments could be repeated and then the results could be described mathematically and compared. Now Galileo believed that all objects fall at the same rate, but it was difficult for him to prove this as free-falling objects fell too quickly for him to take accurate measurements in the time, as he only had a water clock, and the air resistance also affected the rate at which objects fall. So Galileo measured the time a ball took to roll down a smooth groove in an inclined plane. Rolling the ball down a plane slowed the ball's fall as well as reducing the effective air resistance. So as the ball goes down the slope it accelerates. So by rolling the ball along different fractions of the total length of the slope, he found that the distance the ball travelled was proportional to the time taken squared, and that the ball was accelerating at a constant rate. Now Newton took this and worked out that this was because all objects were attracted by the same force to the Earth, the gravitational force. So, when an object is in free fall, there's only one force acting upon it, weight. So the resultant force upon the object is weight, or we could say it equals mg. Now according to Newton's second law of motion, we know resultant force equals ma, so we can equate the two terms. So we can say ma equals mg. You'll notice that on either side the masses cancel through, so we can say a equals g. So this tells us that it's very important that acceleration does not depend on an object's mass. The acceleration of an object only depends on the strength of gravity, g, and at the surface of the Earth this does not vary for objects because the Earth has a uniform gravitational field at the surface. So we can say that the acceleration of all objects are the same. Now it's important to note that in this equation we've not considered the effective air resistance. So we can adapt the equations of motion for objects under freefall. So for objects under freefall, we can say acceleration is g and acts downwards, which is usually negative. So we can say a equals minus g. T, the time is always positive. U and V, the two velocities, can be either positive or negative, and the displacement can be either positive or negative. So if we've got an object falling from rest, we can say U is equal to 0 and A was equal to G is equal to 9.81 meters per second squared. So our equations of motion simplify to V equals GT, V squared equals 2GS, S equals a half GT squared, and S equals VT over 2. Now this equation is only true if it has no initial velocity, it's just dropped. Now, if an object is moving downwards, we can say A equals G, which equals 9.81 meters per second squared. We know V equals U plus GT, and S equals UT plus a half GT squared. V squared equals U squared plus 2GS, and S equals U plus V over 2 times by T. Whilst if an object is moving upwards, it is the same equations again. However, now our G is minus 9.81 to indicate it's accelerating in the opposite direction, okay, to the effect of the gravitational field. So let's have a look at an example question. A ball drops 85.6 centimeters from an electromagnet to a trapdoor in 0.421 seconds. Calculate a value for G. So we write out our SUVAT, S, U, V, A and T. We know S is 0.856 meters. U is 0 because it's dropped. V we don't know. G we need to work out, and T is equal to 0.42, so we can use the equation S equals a half GT squared, or AT squared, so therefore G or A is equal to 2S over T squared. Pop in our values and we get 9.66 meters per second squared. Now it's important to note that this value will not be accurate, as there will be a presence of air resistance as the object falls, and also there's going to be a likely delay in the time of the object falling after it has been released. Now, if you drop a ball or stone, it falls to the ground, and the picture below, based on multi-flash photography, shows the ball at equal intervals of time. So you can see that the ball's velocity increases steadily as it falls because the spaces between the images of the ball increase steadily. So you can conclude the ball is accelerating. So a multi-flash photograph is useful to demonstrate that the ball accelerates as it falls. Usually objects fall too quickly for our eyes to be able to observe them speeding up. Now, if we measure the acceleration of a free-falling object on the surface of the Earth, we find a value of about 9.81 meters per second squared, and we give it the symbol G and call it the acceleration of freefall. Now, if we drop an object, its initial velocity will be equal to 0, so how far will it fall in time t? Well, we use our equation of motion, S equals ut plus a half at squared, which tells us that S equals a half times by 9.81 times by t squared, so it's 4.9 times by t squared. So by timing a fallen object and measuring its displacement, we can determine G. So we know S equals a half gt squared, so if we measure S, we measure t squared, we can use this to determine G. So that brings an end to our lesson today. So we've looked at the acceleration G of freefall. So if we've been successful and learnt in this lesson, we should be able to understand that an object in freefall experiences an acceleration of G. We can explain why an object in freefall undergoes constant acceleration, and then we can also calculate values for an object in freefall as it moves down. So that brings an end to our lesson today on acceleration due to freefall, which is part of the forces and motion module in the subtopic of motion for OCR A-Level Physics. Thank you so much for watching and have a lovely day.